Hello everyone, this is Professor Roman. Welcome to the 33rd lecture in my video lecture series, An Introduction to Discrete Mathematics. In this video, we are going to start our look at Chapter 7, Advanced Counting Techniques. Now this chapter is going to be a bit more challenging than previous chapters. The good news is that it's really optional. My view of elementary discrete mathematics does not require this material. Now the next chapter, Chapter 8 on graph theory, is essential to elementary discrete mathematics. But I thought I would include this chapter, which is not in my original hardcover book, but I thought I would include it in this video series because it's easy enough for you to skip if you want to. So I would suggest, if you have any interest at all in this material, to take the plunge, see how it goes. If you find it too uninteresting or too frustrating, you can just skip the rest of the videos until you get to the videos on Chapter 8 on graph theory. So I want to begin by talking about distributing balls into boxes again. In an earlier chapter of the book, in earlier videos, we discussed distributing both distinguishable and indistinguishable balls into distinguishable boxes. And I did not cover the case of indistinguishable boxes simply because it was more complicated, so I postponed it to this chapter. So we're going to look at the indistinguishable box case now. It's my impression that students have a little trouble with the concept of indistinguishable boxes. One of the problems is if you draw a picture of the boxes, you have distinguished them by their location on the page. That is not the kind of distinguishability that is relevant to this discussion. That doesn't matter. Neither do the contents of the boxes matter as far as distinguishing the boxes. If you have two boxes, one has, say, ball number 1, the other has ball number 2, it's certainly true that the boxes are distinguished by their contents. But again, that's something you have to set out of your mind. That's not distinguishability of the boxes. It's distinguishability of the contents. Okay. So I think maybe the best thing to do is start with an example that compares the cases of distinguishable and indistinguishable boxes. Throughout this discussion, the balls will be distinguishable and labeled with integers 1 through k if they're k balls. Okay. So suppose, for example, we have 5 distinguishable balls numbered 1 through 5 and 3 boxes. If the boxes were distinguishable, and they would be labeled, say, box 1, box 2, and box 3, then one distribution of the 5 balls would look like this here on the left side of this vertical bar. And you would read this to someone else simply by saying box 1 contains balls 1 and 3, box 2 contains ball 5, and box 3 contains balls 2 and 4. It's very simple. On the other hand, if the boxes are indistinguishable, you can't refer to the boxes by name. They're not labeled. So all you can say is one of the boxes contains balls 1 and 3. One of the boxes, or if you want another box, contains ball 5, and one of the boxes contains balls 2 and 4. If someone asks you which box contains balls 1 and 3, you'd say, I don't know, I can't distinguish between the boxes. All I can tell you is that one of the boxes contains those two balls. How do you describe that more mathematically? It looks like this on the right side of this vertical bar. This is set notation, and each element of the set is a subset of the contents of one of the boxes. So you could read this as one of the boxes contains, let me see, I wrote this here. One of the boxes contains 1 and 3, one of the boxes contains 5, and one of the boxes contains 2 and 4. But this set P, which is the set I have up here, is just a partition of the set of ball labels into 3 blocks, corresponding to the 3 boxes. But we have to be a little careful here in thinking of distributions as partitions, because in a partition the blocks cannot be empty, but in a distribution the boxes can be empty, unless we require otherwise. So just to be clear on this, consider a different distribution. One of the boxes contains balls 1, 4, and 5. One of the boxes contains balls 2 and 3. One of the boxes is empty. That would correspond to this partition of the ball label set, 1 through 5, into 2 blocks. We can't write it this way, because, including an empty block, because empty blocks are not allowed in partitions. So, in general, each distribution of k distinguishable balls into n indistinguishable boxes corresponds to a partition of the ball label set into at most n blocks. The number of blocks will be equal to the number of non-empty boxes in the distribution. So it's got to be at least 1, okay, but it can be at most n. If we require that no box be empty, which we're going to do, then each distribution corresponds to a partition of the ball label set into exactly n blocks. By way of notation, in the discussion that's coming up, I'm going to use this set ZK to be the labels, to contain the labels for the balls. They'll always be distinguishable. And I'm going to denote the set of all partitions of ZK, the ball label set, that have n blocks by this symbol. So what we have learned is that the distributions of k distinguishable balls into n indistinguishable boxes with no box empty are in one-to-one correspondence with the partitions in this set. Okay. The partitions of a set of size k, in this case zk, into n blocks. This number, the number of these types of partitions, is denoted by uppercase S, Kn, and it's called a Stirling number of the second kind. So here it is in symbols. Skn is the size of this set, the number of partitions, frankly, of any set of size k into n blocks. So the number of ways to distribute k distinguishable balls into n indistinguishable boxes with no restrictions on empty or non-empty is the same as the number of partitions of a set of size k into at most n blocks. So we take the sum. And I'll use this notation. I don't think I'm going to use it again, but I just wrote it here. Okay. This would be the set of partitions of a set of size k into at most n blocks. The Stirling numbers SNK, or SKN, are named after a mathematician named James Stirling, who investigated them back in the 18th century. But there was some hint that these numbers were in some form or other discussed much earlier than that, even in medieval times. As this definition kind of implies, there were also Stirling numbers of the first kind, and those are denoted with a lowercase s. And I'm going to discuss them in the next video. Note also that SKN is 0 when k is less than n. A set of size k cannot be partitioned into more than k blocks, because then a block would have to be empty, which is not allowed. Also, it's customary to set these initial conditions. We'll talk about that. We're going to talk about a recurrence relation in a few minutes. And these are some simple values for the Stirling numbers that I will leave you to think about. Okay, there is a recurrence relation for these Stirling numbers. I'm not going to keep saying of the second kind, because these will always be of the second kind in this video. So we can reason out this recurrence relation as follows. Imagine a partition P of zk into n indistinguishable blocks. And consider the integer k, one of the ball labels. There are two possibilities. Either k lies in its own block of the partition, so that would be a singleton block, or else k lies in a block that contains other members of zk. These possibilities are exhaustive. It has to be one or the other, and they're mutually exclusive, no overlap. If the partition P contains this singleton block, then if we toss out the block, we get a partition of z k minus 1 into n minus 1 blocks. But we can restore that singleton block, throw it back in. So we have a bijection here between the partitions of zk that contain the singleton block k and all the partitions of zk minus 1 into n minus 1 blocks. So the number of these partitions that have this singleton block k is equal to this Stirling number. As to the partitions in which k lies in a block that contains other integers, we can construct those by taking all of the partitions of zk minus 1 into n blocks, the full number of blocks, and just tossing k into any one of those blocks. Well, they're n blocks, so there are n possibilities for where to put k. And so the number of these partitions is n times the Stirling number sk minus 1n. These are the partitions where k is not lonely. If we add these two numbers here, we're going to get the full Stirling number. So here is our recurrence. And these are the initial conditions. And from that, we can compute, or a computer can compute Stirling numbers. There is also an explicit formula for the Stirling numbers. And one way to find this formula is to relate the distributions of the k distinguishable balls into n indistinguishable boxes with no box empty to the distributions of these balls into n distinguishable boxes with no box empty. So we relate the indistinguishable box case to the distinguishable box case, which we'll have, as I say, better luck finding the counting that set. Well, how do you turn indistinguishable boxes into distinguishable boxes? If there are n of the boxes, all you do is you label the boxes 1 through n, and that now they're distinguishable by their label. And you can do that in n factorial different ways, depending on where you scramble the labels. So in the language of partitions, there are n factorial times more labeled partitions, and by that I mean partitions in which the blocks are labeled and so distinguishable, so they're not really partitions. And the label set would be Zn, because there are n boxes or n blocks. There are n factorial times more of these than there are ordinary partitions. As far as I know, there is no name for partitions in which the blocks are distinguishable. So labeled partitions seems as good as any term. So the number of labeled partitions is n factorial times skn. On the other hand, a labeled partition can be viewed as a surjective function. All it does is maps the ball label to the block label of the block that contains that ball. If you think of, you have these blocks and they are labeled and each one contains a certain number of balls. If you think of this function, it's just the address function. If you think of the label of the block as the address of each of the balls inside that block, then this function just gives the address of each ball. When you strip all the irrelevancies away, just for counting purposes, we're just talking about surjective functions from the ball label set to the block label set. So just to illustrate, because I know this can be confusing, believe me. A lot of students are confused by this. It takes time, it takes persistence. Remember this partition we talked about earlier. We're distributing 5 balls into 3 blocks. I'm going to take out this word boxes here because the blocks and the boxes are not exactly the same, because the empty boxes don't correspond to a block. The non-empty boxes correspond to the blocks. Well, there are 3 factorial ways to label these blocks. Here are 2 examples. I'll just use subscripts for labels, 1, 2, 3 or 3, 2, 1. These are different labeled partitions. They're the same partition. The address function I'm talking about for P1 here will map the integers 1 and 2. The ball labels 1 and 2 get mapped to the address 1. And the ball label 3 gets mapped to address 2, or has address 2. The balls 4 and 5 have address 3. And you'll get a different function for P2 by reversing the images here, 1 and 3. Well, this viewpoint is just what we need because we've already determined how to count surjections. We did that quite a while ago using the principle of inclusion-exclusion. That was theorem 300, so we're up to 361, so that was quite a while ago. But it tells us that this number is equal to this sum, which I'm rewriting a little bit here. And so we divide by n factorial, and we get a formula for the Stirling numbers of the second kind. It's the typical inclusion-exclusion type of formula. It's a summation, not all that pleasant, but still a formula. Now, the Stirling numbers of both types are very important in the theory of counting. They have a lot of applications. They appear in a lot of places. For example, you might recall that we discussed the lower factorial, also called the falling factorial. K lower factorial n is this product here, starting with k. Each factor goes down by 1, and there are a total of n factors. And we defined this for non-negative integers n and k. But this definition applies equally well to any real number in place of k here, not n, but k. So if I call that number x, x lower factorial n is this product. This is in fact a polynomial of degree n. Analogous to the lower factorials are the upper factorials, also called the rising factorials. And they look like this, the same pattern. Start with x, but you increase each factor by 1, and there are n factors. There's actually a simple relationship between the upper and lower factorials. X lower factorial n is this. If we factor out a negative sign from each factor, negative 1 to the n, we have negative x plus 1, and so on. It looks like this. So we can connect the lower factorials with the upper factorials in both directions. Okay. I'm going to use this once later on. Other than that, it's not critical for us. The Stirling numbers of the second kind provide a connection between the sequence of powers of x, x to the nth power, and these two sequences of upper and lower factorials. And here's what that looks like. X to the k is the sum from 0 to k. N goes from 0 to k of Stirling number skn times lower factorial, x lower factorial n. So that's the Stirling numbers here are the coefficients that connect the powers of x to the lower factorials. It's two sequences of polynomials, the powers of x and x lower factorial. This is a common thing that people like to do in applied mathematics, is connect two polynomial sequences. And we can reverse this, we can change this to upper factorials this way. This equation follows from this one, and I'll let you sort that out. So let's prove this equation. And I'm going to do it, I'm going to give a combinatorial proof, because I think that's the most interesting. First, notice that this is a polynomial of degree k, and so is this, and I'll let you figure that out, why that's true. So the difference between these two polynomials is a polynomial of degree less than k, because both of these polynomials are monic. This one's obviously monic, but this one is as well. So when we subtract, the leading terms cancel, and we get a polynomial of degree less than k. So if we can show that this equation holds for the k values 1 through k, so set x equals 1 through k, then we know this equation holds for all real numbers x. That's something also to think about. I shouldn't give you a hint, but I will. If you have a polynomial of degree 5 and it has 6 zeros, or let's say a polynomial of degree up to 5 or less, and it has 6 zeros, what can you conclude? So we can let m be one of these numbers, 1 through k, and just an arbitrary number, and show that this holds. And I've taken the liberty of rewriting this a little bit, and you'll see why in a minute. Instead of x lower factorial, well, let's say m lower factorial n, I've got m choose n, so I have to multiply by n factorial. And the reason is because we're already familiar with this. This is the number of surjections from zk to n, okay. Or in fact, the number of surjections from zk to any set of size n. The elements of the set have no bearing on the sizes here. So suppose we have a subset of Zm of size n, call it I. Then for each of the n factorial skn surjections, say f from zk to I, we can upgrade the codomain. Now it's only the codomain, not the image. We're not changing the image, we're not changing the domain, we're not changing the rule that maps elements to elements. All we're doing is pretending the codomain is all of Zm. Okay, this is a very minor change in a function. Technically, it's a different function because it has a larger codomain. For example, if we map f of x to, if we map x to x squared, we map real numbers to real numbers, and we decide, I think I'd rather think of this as a function from real numbers to complex numbers, I can do that. It's a change in the function, but not a serious one, because you can always back down. You can always reverse the process and think of the think of the function as having a smaller codomain. As long as the codomain contains the image, you're not doing very much to the function. So I call this f over bar here. F bar is the same as f, except I changed I went from the image, the codomain was the image, because the function was surjective, and I replaced the codomain with Zm. It's no longer surjective unless I happens to equal Zm, but it's in other respects the same function. So I can go back and forth between these two. This is a one-to-one correspondence. Downgrading is the inverse of upgrading. Downgrading all the way to the image. Okay. Well, there are m choose n subsets of size n, okay, that we could use as images. And for each of these subsets, there are this many surjections from zk to I, the image, and therefore there are this many functions from zk to zm that have I as their image, the upgraded functions. So there are this many, I've now multiplied by m choose n, functions from zk to zm whose images have size n. I don't know what those images are. They're the letter I, ranging over all subsets of size n. Okay. Finally, if we sum on n, the size of the image of the functions, we get this sum. But we now have the number of all functions from zk to zm broken down first by the size of their image and then by the actual image itself. But the number of functions from zk to zm, no restrictions, is m to the k. So that's right here. Again, I understand this is a relatively complex argument, so it may take a little while for it to sink in. Finally, we saw earlier that the number of ways to distribute k distinguishable balls into n indistinguishable boxes is the same as the number of partitions of a set of size k into at most n blocks. At most, because blocks have to be non-empty, boxes can be empty. And that was this sum. Because S0I is 0 by convention, we could drop this lower sum to the lower limit of summation to 0 if we want. Also, as to the upper limit of summation, the number of blocks in the partition cannot exceed the size k of the ball set, because otherwise you'd end up with an empty block. So if I kick this up to k, then this summation from 0 to k of ski, which I call, and so do a lot of others, b sub k, is the total number of ways to partition a set of size k, where we're not considering putting no unnatural restrictions on the number of blocks. Any number of blocks is fine. Total number of ways to partition a set of size k. That is a very important number. It is called a Bell number, and it's named after a mathematician named Eric Temple Bell, not the inventor Alexander Graham Bell. Okay, so these are the Bell numbers. They count the number of partitions of a set of size k. And they're not exactly simple numbers. You can stick this formula we had, this formula, and you have to have another summation, and it's going to be a bit of a mess, but that's life. Okay, that concludes our discussion of Stirling numbers of the second kind and their relation to partitions. Thanks for hanging in, and I hope to see you in the next video where we'll talk about Stirling numbers of the first kind.